Hello everyone, this is Roushan and today I will be discussing week 10 lectures. So in the last session I have conducted the problem solving session for week 9 in which we have discussed about different kinds of torsion, okay, and we have solved some problem related to torsion. Uh, in this session we will be discussing week 10 in which we have 3 lectures which is based on shear center and theory of beams. So let's start the today's session. So week 10. So in week 10 we have 3 lectures, that is concept of shear center, theory of beams, and beam buckling. So we will be studying about these concepts which is related to shear center, theory of beams, and buckling of beams. So first of all, I will briefly give the overview of these 3 lectures in a short view so that you will be able to solve questions related to this concepts. So then after completing the briefing, I will then discuss about I will then solve some problems related to buckling of beams and bending energy and shear center. Okay. So in the first lecture, which is basically based on shear center. So in this, already in the lecture, all the derivation has been derived. So you can go through that lecture to see the overall concept behind the shear center. So I just tell you that shear center basically is the point in the cross-sectional plane where the net torque due to shear distribution is 0. So at the, and one thing I write here about the definition of shear center. Shear center. So according to the definition, the point in the cross-sectional plane, the point in the cross-sectional plane relative to which the point in the cross-sectional plane relative to which the net torque due to shear stress distribution vanishes. Due to shear stress distribution vanishes. Okay. And one thing I also like to mention here that for a symmetrical body, shear center always lie in the line of symmetry. Okay, so suppose we have this type cross section. The cross section of a body is of this type. Sorry for the disturbance. I think there is some power cut here, so that's why the network get disrupted. So I am talking about the symmetry of a cross section. So any beam which has cross section in which it has symmetry, some symmetry, so the shear center always lie in the line of symmetry. So suppose we have some cross section like this. So here you can see that we have 2 line of symmetry. First one is this one and the second one is this one. So it has a common point, that means shear center always lies at this point. Okay, so for a symmetrical cross section, the shear center always lie in the line of symmetry. Okay, so this is about shear center. So I just write here, shear center always lies, sorry, shear center always lies on the line of symmetry of the cross section, on the line of symmetry of cross section. Okay, now coming to the next lecture, which is based on the theory of beams. So in this lecture we will be discussing about different kind of bending formula. So basically in this course we will be using two different bending theory. That is, the first one is Euler-Bernoulli beam theory, and the second one is I think someone has raised their hand. So yes, you can unmute yourself so that I can listen you. If anyone have any doubt, please let me know. Okay, so I mean here I am saying that for so in this course we have basically two bending theory. The first one is Euler-Bernoulli beam theory, and the second one is based on Timosenko beam theory. And this using these two theories, we will solve some numerical problems later on. So let's start from the Euler-Bernoulli beam theory. So Euler-Bernoulli beam theory. So the basic assumption of this theory is that the center line tangent and the cross section normal are aligned with each other. Okay, so with this condition, with this main assumption, we have only one independent variable here, that is the deflection y. So based on that, we have one bending formula. So here bending formula is given by m is equal to ei kappa. Okay, so in Euler-Bernoulli beam theory, we will be using this formula, m is equal to ei kappa, where m is bending moment, ei is basically bending stiffness. So E represent the material property and I represent the geometry property of the material. So this is the whole combination gives us bending stiffness. And the third one is kappa, which is nothing but the curvature, bending curvature. Okay, and the curvature you can find out the curvature using the basic formula, that is del 2y by del x square upon 1 plus del y by dx del x whole square to the power 3 by 2. So this is the formula to find out the bending curvature due to bending. And after several assumption, basically we are assuming that the slope is very small, very small relative to the length of the beam. So after assuming that is del y by del x is approximately equal to 0. After assuming this, we can reduce this curvature formula, which is nothing but it will become approximately del 2y upon del x square. So finally the bending formula will become ei d2y upon dx square is equal to mx. So this is our main bending formula that we will use in the upcoming problem solving session. Okay, So this is all about Euler-Bernoulli beam theory. So in this Euler-Bernoulli beam theory, we have three assumptions. The first major assumption, I already told you, that the cross-section normal and the center line tangent are aligned with each other. The second assumption is axial displacement of the beam is negligible, and due to that only the x, that is a deformed x, basically we are assuming that it doesn't change after deformation. So small x will become big X, that is undeformed coordinate. And the third assumption is slope of the beam center line is negligible, and due to that this assumption is there, that is del y by del x is approximately 0, that is the slope of the deflection is approximately negligible. So with these three assumptions we will find the uh, bending formula in Euler-Bernoulli beam theory, that is EI d2y by dx square is equal to mx. Okay, so this is all about Euler-Bernoulli beam theory. The next theory that is in the syllabus of you is the Timoshenko beam theory. Timoshenko beam theory. So in this theory, we are assuming that the cross section remain rigid, but the cross section normal and the central line tangent are not aligned with each other. They are basically making an angle, making some angle with each other, so they are not constant. Okay, sorry, they are not aligned with each other. So this is the main difference between the Euler-Bernoulli beam theory and the Timoshenko beam theory, and due to this we have two independent variable in Timoshenko beam theory. The first one is deflection and the second one is theta, that is the rotation angle of the cross section, that is rotation of the cross section. So here we have two independent variable, y and theta. So and therefore we need two different equations to solve for these two unknown. So the first equation is EI kappa equal to m, which is also in the Euler-Bernoulli beam theory, and dy by dx equal to, sorry, minus theta equal to v upon kappa ga. So this is our second equation. And here one thing I would like to mention here, k kappa, that is curvature, here not equal to d2y by dx square, because here the cross section normal and the center line tangent are not aligned with each other. They are making some angle. So this is the formula. So you can write here from this equation that EI d theta by dx, that is not equal to d2y by dx square. EI d theta by dx equal to mx. So this is these two formula we are going to use for solving the numerical problem. So this is these are the two equations. These are the two equations for the Timoshenko beam theory. Okay. So this is all about the Timoshenko beam theory and Euler-Bernoulli beam theory. So I just give the brief overview of these two theory. You can go through the lectures where a detailed derivation is already done, and you can see that derivation to better understand this theory, how it comes to final expression, this final expression. So this is all about the bending theories, and the last topic that is covered in this lecture is the beam buckling. So there is a buckling formula. So there is a buckling formula to find the critical buckling load. So that is given by P critical, that is the critical buckling load is given by pi square EI upon 4L square. So this is the formula for beam buckling. Okay, so I think I am audible. So this is a critical buckling load formula where L is the length of the column. L is the length of the column and P is the critical buckling load, where, so this is not the buckling formula, that is basically buckling of column. So in this we assume that there is no shear stress present, because we are assuming that the slenderness ratio of this column is very high, that is the length to cross section ratio is very large. So that's why we are using the this formula. We will be using this formula only for a very long column. So yes, so this is a formula for the critical buckling load. So you can see from the here that critical buckling load is directly proportional to the bending stiffness EI and inversely proportional to the square of the length of the column. So we will use this concept to solve some numerical problem based on the buckling of column. So this is all about today. So this is all about the concepts behind week 10. Now I will going to start the problem solving session where I will solve some numerical problems. So let's start the problem solving session. So the problem number 1, which is basically based on the shear center. So the question is, think of a beam whose cross section think of a beam whose cross section has the shape of a thin annular disc but having a cut along a radial line along a radial line on z axis. How will the shear stress distribution shear stress distribution how will the shear stress distribution be in the cross section? Okay. The next question is, will such a beam undergoes just bending or it can also twist? The question is, I am repeating the question. That is, think of a beam whose cross section has shape of a thin annular disc but having a cut along a radial line on a z-axis. So the question, so I'm drawing the figure. So we have a circular beam. Sorry. Yeah. We have a circular beam and there is a cut. Okay. So we have a circular cross-section shape beam of a thin annular disc or having a cut along a radial line. So I just draw the figure here. So the question says that there is a cut. So yes, there is a cut here, and we have to find the shear stress distribution in the cross section. And the next question is asking that such a beam undergoes just bending, or it can also twist. So for this we have to find the shear center for this problem, whether the shear center whether the shear so for the twisting case, the shear center must lie outside the cross section. So you can see that here the shear stress distribution. So first of all, this is our line of symmetry for this problem. So as I told earlier, that if any cross section have any line of symmetry, then shear center must lie on that line of symmetry. And the shear stress distribution in such cross section is of this type. So this is the shear stress distribution for this cross section. And from the definition of shear center, it is already so that for shear center to exist, we have net torque about that point must be 0 due to all shear stress. So you can see that if we draw, so in this green region, if we take uh, the torque about this line of symmetry, you can see that all the shear stress, due to all the shear stress, the torque will add up. Not they are not getting cancel out, because all the shear stress are in the same direction. So in the green region there is no shear center, because there is no net torque 0 in that region, in that line of symmetry region. So we can say that the shear center must lie outside the cross section. So we are assuming that it is somewhere here. It is somewhere here. That is, the shear center lies somewhere here. So we are just assuming, and we have to find that whether it lies here or not, and what is the distance from the center. We have to also find that what is the distance of that from the center. So let's begin the problem. So I'm drawing the figure one more time. So suppose the thickness of the cross section is T, and here we are taking some arc length S, and this is our center, which is O, and here we are taking one point, that is P naught, that is P naught, and this is our axis. Suppose this is Z axis and this is Y axis. Okay, so we are assuming that shear center lies somewhere here. So this is the point for the shear center, and we have to find out that point. Okay, so in the lecture itself, the derivative of shear center, the formula for the shear center is already derived in the lecture, so I am using just that formula, that is z coordinate of shear center is given by this equation, that is delta z equal to 1 by izz integral over 0 to 2 pi r er hat cross qy a e hat theta dot I hat, which is also equal to r square upon I z z 0 to 2 pi q1 q theta of y into d theta. Okay, so we have to find qy. What is the value of qy? So qy is the basically y bar into dA. So y bar is the centroidal position of the cross section and A is the uh, area of the section. Okay, so we have to find out the dqy, which is given by y bar into dA. So for that we cut a section here. We cut a small section using this figure here. So suppose it making at angle phi, and this is the complete angle theta, and this is our d phi, and the radius, the mean radius of this of this circular disc is r, and this is the arc length s. Sorry, this is arc length s, and t is the thickness for this cross section. Okay, so the area of this section, this small section, is given by dA is equal to t times r d phi. Okay, t into rt d phi. And what is the distance here? So this distance is given by r sine phi. Okay, r sine phi. So y bar is the distance from the centroidal distance of this section from the line of symmetry. Okay, so dqy then given by y bar into dA. What is y bar here? R sine phi into dA. What is dA here? R d phi, which is equal to r square t sine phi d phi. Now we have to find the total qy, that is integral of qy. Qy theta is equal to integral of 0 se theta dqy, and dqy here is integral of 0 se theta, r square, and t is constant, so it is taking out of the derivative, sorry, integration, then sine phi d phi. So r square sine phi, integration of sine phi is minus of cos phi 0 to theta. So cos theta and cos minus 1, cos 0 is 1, so r square t 1 minus cos theta. So this is the formula for Qi. And the next thing that we need is IZZ. That is the polar moment of inertia, polar moment of area about z-axis. So it is given by IZZ. IZZ is given by 1 by 2 of I-axis, because from the perpendicular axis theorem, Ixx plus Iyy equal to Izz, and here Ixx equal to Iyy, so 2 times Ixx equal to Izz, so Izz equal to, sorry, here actually xz yz is in the plane of cross section, so Izz plus Iyy equal to Ixx, which is equal to Ixx, and here it is Izz. So Izz equal to Ixx upon 2. And what is the polar moment of area? Second polar moment of area about x-axis is given by half r square into 2 pi rt. Okay, which is given by r square, sorry, r cube, 2 to cancel out, pi r cube t. So this is the Izz. Now we have to find the delta z, that is the z coordinate of CL center. So delta z is given by integral over, so what is r square by Izz? I am copying directly from here. So delta z, that is the z coordinate of CL center, is given by this equation. So r square by Izz integral over 0 to 2 pi qy theta d theta. So yeah, so qy is, okay, so r is square by pi rt r cube t, and qy is, here qy is r square t by into 1 minus cos theta. So into r square t, I taking it out because it is a constant, so r square t integral over 0 से 2 pi 1 minus cos theta into d theta. So dt cancel out, r to the power 4 cancel out with r, so r by pi, and this will become theta minus cos theta integration is sin theta 0 to 2 pi, r by pi 2 pi, what is sin 2 pi? Sin theta of 2 pi is 0 minus 0 plus 0, so that is r by pi in Okay, so delta z is given by 2r. So the position of the shear center from the center of this cross section is given by delta is given by 2r. So we have found the position of shear center, that is distance of 2r, 2 times of radius. Now the question says we already found the shear stress distribution. Will such a beam undergoes just bending or it can also undergo twist? So for twist to happen, we basically apply shear force so that beam does not induce any twist. So yeah, we have to, for no twist, that is for no torque to happen, we must apply the shear force along the line of action of the shear center. So here you can see that we found that the shear center is located at a distance of 2r, which is outside the cross section. So at this point we have to build one rod, and about this line we have to, sorry, yeah. So if I draw this figure in 3D, so suppose, sorry, so suppose this is our radius. So basically from here we have to build one rod, a thin rod, and apply the shear force along this direction. So this is the point of the shear center, and we have to apply the shear force at this line of center. Okay, we have to apply the shear force along the direction of the shear center, and here is our shear center. So if we apply shear center, such that its line of action passes to the shear center, so it does not this beam does not induce any twist. Okay, so this is all about question number 1, which is to find out the shear center and check whether the beam induces twist or just bending. So this is all about question number 1. Now coming to problem 2. Now coming to problem 2. So the problem is, this question is also based on shear center. So actually a noise is coming from outside, so I think uh, please wait for some time. Till then, sorry for the noise. So the next question is, think of a beam having thin and open cross section. Think of a beam having thin and open cross section. The shape of the cross section is shown in the figure. the shape of the cross section is shown in the figure. Suppose the beam is subjected to transverse load. Suppose the beam is subjected to transverse load at one of its end such that the force applied is along y-axis. Such that the force applied is along y-axis. So the question is, where should the load be applied in the cross sectional plane at the tip so that the beam does not twist. So that the beam does not twist. So this question is basically to find out the shear center, location of shear center, because the shear center is the only location where the beam, about which the beam doesn't twist. So I am repeating the question. Think of a beam having thin and open cross section. So the question is also have a figure. So I am drawing that figure. So this is the figure for this question. So the question is, think of a beam having thin and open cross section. The shape of the cross section is shown in the figure. The cross section is of C type. Suppose the beam is subjected to transverse load at one of its end. So there is a transverse load acting at the ends of the cross section, and such that the force applied is along y-axis. So the force is applied along the y-axis. So the question is, where should the load be applied in the cross-sectional plane at the tip so that the beam doesn't twist. Okay, so the question is asking for where should the load be applied in the cross-sectional plane at the tip so that the beam doesn't twist. So at the tip, that means this is the region where the force is applied, and where it will be the location of the shear center, because at that point only there is no twist. About that point only there will be no twist. So the load, if the load is applied along the axis of the shear center, at the shear center along the axis, that is the load, suppose from here at the tip of this cross section anywhere, suppose we are applying load, and that load have passes through the shear center, then there will be no twist in the entire cross section, because the concept of shear center says that whenever any load or any shear force acting such that it passes through the shear center, then the beam does not undergoes any torsion, or we say twist. So we have to basically we have to find the location of shear center. So let's start this problem. So the first of all, this is a very thin tube where thickness is very less than A. So we can say that here thickness is very less than A. So shear stress tau Sx is given by V times, this is a shear force acting, Qsy upon Izz into T. Okay, so this is for the shear stress distribution for thin cross section. Now, so here we are assuming we have two domain of the cross section. The first one is this one, and the second one is, suppose, this one. Yeah, and we have two, and here we have two this type of cross section. So basically we found the second moment of area of any one, and we multiplied it by 2, then we get the total second moment of area for this cross section. So first of all, the upper part, for the upper part, tau Sx is given by V times A by 2, because the distance from here is, this distance is A, and this distance will become A by 2. So A by 2 into S into T. What is S here? So S is the distance S is the distance from here only, A by 2 into S into T upon Izz into T, which become VAST upon 2 Izz into T. Now for the second one, for this one, for this part, so suppose this distance is somewhere H S. So for this cross section we have tau Sx for the upper part and this is for the middle part. For the middle part. We have tau Sx equal to V times first the distance. So the distance is S plus A by 2 minus S. This distance is A by 2 S plus A by 2 minus S upon 2. S plus A by 2 minus S upon 2. And then the area. So what is the area of that one? A by 2 minus S into T. A by 2 minus S into T. So this is the area. Upon IZZ into T. Okay. So on solving this, we will get V times A square by T by 2 plus half of A square by 4 minus S square times T upon IZZ into T. Now for the lower part. For the lower part, we have tau Sx equal to VQ upon IZZ into T, which is basically V times first the location, that is A minus of A by 2 minus A by 2 into S into T upon IZZ into T, which is equal to minus VAS upon 2 times IZZ into TT cancel out. So minus VAS, here also TT cancel out. So it becomes VAS upon 2 times IZZ. Here it becomes minus VAS upon 2 times IZZ. Now we have to find the torque, total torque. So first of all, we have to find the second moment of area for the upper part and the middle part and the lower part. So for the upper and the lower part, we have same second moment of area. So IZZ for upper and lower part. So it is given by 1 by 12 AT cube, A cube T. Okay, and IZZ of the middle part is given by So for the upper part, we have to use parallel axis theorem because we know about this axis. We know the value of IZZ about this axis, but we have to find the value of about this axis. So we have to apply the parallel axis theorem, which is given by 1 by 12 AT cube plus AT into A by 2 ka whole square. And because upper we are solving for the both upper and the lower part, so that's why we have to multiply it by 2, because the upper and lower part have same second moment of area and we are adding it up. And for the middle part, we have only a straight segment and the centroid of that cross section lie in the axis of symmetry, so that's why it simply become 1 by 12 A cube T. Okay. Now to obtain shear center, torque due to first we have to obtain torque due to shear stress distribution about origin. Okay, so torque first on the upper part plus middle part plus lower part. So upper and the lower part we are simply adding it up. So VAT upon 2 IZ 0 to A SDS cross A by 2 into 2 because these two are same. Plus 0. Why 0? Because the shear stress distribution, if you take the torque about this axis, about this line of symmetry, about this axis, so basically you are taking the torque about this axis, the red one of this cross section about this axis, so it ultimately coming out to be 0. So therefore torque due to middle one is 0. So the final equation become VA 4T upon 8IZZ into 2, which is equal to VA 4T upon 4 times total, that is T square by 6 total IZZ, yes, T square by 6 plus 7 by 12 A square. If we add it up, it will give us, so where it comes, total IZZ equal to 1 by 6 AT cube plus A cube T into 7 by 12. And using this, we find the value of this one, total IZZ. Okay. Now we have to find the location of shear center. So we know that any shear stress distribution which passes through the shear center does not undergo any twist. Okay, that means twist to be 0. That means this equation must be 0, so that the shear center, to find the location of shear center. So the location of shear center is given by A cube upon 4 T square by 6 7 by 12 A square. Okay, and from where it goes, from the negative z-axis, along negative z-axis. So the shear center is located this amount by along the negative z-axis. So somewhere here it lies. because this is the positive direction. Yeah, so this is the positive direction, and this is the positive direction, and this is the negative direction. So along negative z-axis here, center lies somewhere there. So this is all about question number 2. Now coming to problem number 3, which is based on theory of beams. So the question is, suppose a beam is kept with roller support. Suppose a beam is kept with roller support at one end where x equal to 0, constrained to only move in y direction. Constrained to only move in y direction. And pinned at the other end. As shown. Beam is subjected to transverse load P at the middle of the beam. So the question is, find the deflection of the beam using Euler-Bernoulli beam theory. Find the deflection of the beam. Find the deflection of the beam using Euler-Bernoulli beam theory. Okay. So the here a figure is also there in this question. So I am drawing it. So this is the figure for this question. So the question is, suppose a beam is kept with a roller support at one end, x equal to 0. So there is a roller support here, as you see in the figure. Constrained to only move in the y direction. So it is constrained to move only in the y direction, as shown, and pinned at the other end. And the other end is bent. Actually, beam is subjected to transverse load. So here you can see at the middle of the beam there is a transverse load acting And the question is, find the deflection of the beam using Euler-Bernoulli beam theory. So we have to find the deflection using Euler-Bernoulli beam theory. So first, draw the free body diagram of this full beam so that we can better understand where the forces acting, internal and external forces are acting. So this is the beam, and suppose the end points are A and B here. So in the middle of this beam, there is a transverse long acting upward. This length is L/2. As this is a roller support at the left end, you can see here this is a roller support, so there is a translation happening. So that's why there is no reaction force there, but because you can see that there is no rotation happen, so there must be a moment, reaction moment here. So I am applying one moment here, reaction moment, which is acting like this, moment about A. And here you can see that in the right end the beam is actually fixed. Okay, there is a pin support. So that's because due to this there is some reaction force which is acting upward. So let's suppose Rp is the reaction force. So here we have two unknowns, Ma and Rb, that is moment about A and reaction at B. So for this we need two equations to solve to find these unknowns. So first of all, using the force balance along the y direction, that is summation over Fy is to be 0, and we take upward as taken as positive. So using this we have two forces in vertical direction, that is P plus Rb equal to 0. So Rb equal to minus P. So we found the Rb value, that is a reaction force at B, that is equal to minus of P. Basically it is acting downward in downward direction and the magnitude is P. Now taking moment balance about left end, and we take counterclockwise taken to be as positive. Okay, so from the left end it is given by equal to 0. So here you can see this is in clockwise direction from the left end, so it's negative minus Ma plus, due to this there is a clockwise, actually if we take the moment about the left end there is a clockwise rotation, so P into L/2 plus Rb is also upward, so it is also plus, but here we find it is minus P, so minus of P into L equal to 0. So it finally becomes Ma equal to minus of PL/2. Okay. Now we are using the Euler-Bernoulli beam equation, that is using Euler-Bernoulli beam theory. We have Ei d2y upon dx square equal to mx. Okay, so you can see here that load is acting in the middle in the upward direction, that is P. So we have two different moment expression from the left end and the right end. So one by one we found the moment expression about from the left end, and then we found the moment expression of moment in the, from the right end. So the first case is So here mx in the cross section, that is moment at any point x in the cross section, will have different expression for x less than L by 2 and x greater than L by 2. So start with, so we consider two cases separately. Okay. Here we have a moment applied here. 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 Here we have a moment. Okay. MA. This is point A and this is point B. Here we have a reaction force R of P. And here in the middle there is a load applied of P magnitude. This length is L by 2. So at this point we have Vx, shear force acting downward. Here it is Mx and here it is downward load P acting. So using this FBD, we are assuming that positive Fi is taken as positive and we are taking it as 0. So using this we get Vx equal to minus of P, and from here anti-clockwise is taken as positive. So summation over m about left end equal to 0, which is minus of mx minus of p into L minus x equal to 0. So it becomes mx equal to minus of p into L minus x. So we found out the value of mx from the right end where x is greater than L by 2. Now for the second case, that is for x is less than L by 2. For x is less than L by 2. For this case, somewhere here we are taking the cross section, and this is MA, this is P acting here, and this length is L by 2. This is RB reaction force, RB is acting. This is point B. So if we draw the FBD from the right side, this is mx. Here shear force is acting downward, Vx. There is also a load P which is acting at a distance of L by 2. This is P acting downward. So using the force balance in the y direction, we are taking summation over Fy equal to 0. So it becomes Vx equal to P minus P, that is equal to 0. And what about bending moment? So bending moment about in left side. So it is equal to mx minus of mx plus P into L minus x. Sorry, P into this length is L by 2, right? L by 2, and this length is x. So L by 2 minus x. This length is L by 2 minus x. So plus P into L by 2 minus x. Yeah. This length is L by 2 and this is x. So yes, this length is L by 2 minus x minus P into L minus x equal to 0. So it finally becomes mx equal to P into L by 2 minus of P into L by 2. So we have found the mx from both case, that is from x equal to 0 to L by 2 and L by 2 to L. Now we have to apply the boundary condition to find out the unknowns here. So we have two boundary conditions. Boundary condition 1 is for x less than L by 2, we have slope at x equal to 0 is 0. That means dy by dx at 0 is 0, because you see here that at the left end there is no slope, it is fixed, or only it is translating, so there is no slope. So slope here is 0, and the boundary condition 2 is for x greater than equal to L by 2. For x greater than equal to L by 2, we have displacement at x equal to L is 0. That means y at L equal to L equal to 0, because it is pinned at the right side. You can see in the figure that the beam is pinned at the right end. So that's because displacement is 0 there. Now for x is less than L by 2, we are applying the bending equation, that is EI d2y by dx square equal to mx. And what is for x is less than L by 2, we have already found the value of mx, that is minus PL by 2. EI d2y by dx square equal to minus PL by 2, that is EI, we are taking the first derivative here, first integration here. And in the first integration we will get minus EI dy by dx equal to minus PL by 2 into x plus c1. Again integrating. So first I apply boundary condition using boundary condition 1. what is the first boundary condition? So dy by dx at 0 equal to 0. So using this boundary condition, 0 equal to 0 plus c1, that is c1 here comes out to be 0. Now again integrating this equation, we will get eiy equal to minus pl by 2 x square by 2 plus c2. It becomes y equal to minus pl x square upon 4 ei plus c2. So this is the final expression of deflection. Now for x is greater than equal to L by 2. So for this we are using the Euler-Bernoulli beam theory. So here we found that mx is minus of p into L minus x. Mx equal to minus of p into L minus x. So using Euler-Bernoulli beam theory, ei d2y by dx square equal to minus p into L minus x. Okay. Minus p into L minus x. Integrating one more time, ei dy by dx equal to minus p into L minus x, that is e minus p lx plus px square by 2 plus d1. Again integrating, eiy equal to minus plx square by 2 plus px cube by 6 plus d1x plus d2. So y of x will become minus pl square by 2 ei. If we take 1 by ei is common, we will get 1 by ei minus plx square upon 2 plus p x cube by 6 plus d1x plus d2. Okay, so we can find the value of d1 using the continuity of slope at x equal to L by 2. So at x equal to L by 2 we have same slope from both the side. So dy by dx at x by equal to L by 2 from left end equal to dy by dx at x equal to L by 2 from right end. So from left end it is given by this equation, minus pl upon 2 ei pl square by 4 minus pl square by 4 equal to, from the right end it is given by minus pl l square by 2 plus pl square by 8 plus d1. So it will become d1, from here we find out the value of d1 equal to pl square upon 8. Now here we have to find the value of d2 also. So for d2 we are using the continuity of deflection. This is continuity of slope. And here we are using the continuity of deflection. So y at x equal to L by 2 from the left end equal to y at x equal to L by 2 from the right end. Okay, so if you see the y value from the left end, we already computed there, minus PL x square, that will become minus PL cube upon 16 EI plus C2 equal to 1 by EI minus PL cube upon 8, then PL cube upon 48 plus PL cube upon 16 plus 5 PL cube upon 24. So we have still not find the value of D2. What is the value of D2? So using the deflection, using the BC2 boundary condition, second boundary condition, y at L equal to 0. So it becomes y at L equal to 0, that is minus PL cube by 2 plus PL cube by 6 plus T1. What is T1? PL cube by 8 plus D2 equal to 0. So from here D2 will become 24 minus 3 plus 4 minus 4 plus 12, which will become 5 by 24 into PL cube. Okay, so using this we are calculating here. So 5 by 24 PL cube. So from here we find the value of C2, which is equal to 11 PL cube upon 48 EI. Now what is the question? The question is to find the deflection of the beam. So we have already find the deflection, variation of deflection along the length of the beam for the two different parts. First from x equal to 0 to L by 2, and the second part is for the x equal to L by 2 to L. So the deflection variation of deflection along the length of beam is given by y at x, which is a function of x, minus PL x square upon 4EI plus 11 PL cube upon 48 EI for x less than L by 2. 1 by EI minus PL x square upon 2 plus px cube upon 6 plus PL square upon x upon 8 plus 5 PL cube upon 24. This is for x greater than equal to L by 2. So this is the final deflection equation for this problem. So this is a very good question related to Euler-Bernoulli beam. So here I am just give the overview what is the question here and how we solve such type of question. So first of all, this is a question based on the beam pinned at the other end and constrained to roll only at the left end. And here we have to find the deflection of the beam using Euler-Bernoulli beam theory. So first we have to see the effect of stress distribution. That is, we have to see the deflection and the moment variation. So we have to use the moment balance equation and the force balance equation at all the cross section. So you can see that here in the middle of the cross section, here we have a load. So we have two different expression for deflection as well as slope from the left side and the other, right side. So from 0 to L by 2 we have different expression for deflection, and from L by 2 to L we have different expression for deflection. And therefore we are using the concept that we break the question into parts. First we have to find the deflection variation from 0 to L by 2, and then we have found the deflection variation from L by 2 to L, and then we combine both the deflection variation, and therefore after computing this we reach out to the final solution that is given by this one. So I hope you understand this question. This is a very good question based on the beam bending. Now move on to the next question, which is also based on the beam theory of beams, but here you have to apply the Timoshenko beam theory instead of Euler-Bernoulli beam theory. So I am writing the question now. That is question number 4. So the question is 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 so the question is for the beam shown find the reaction moment find the reaction moment sorry find the reaction moment and deflection at A using use Timoshenko beam theory. Use Timoshenko beam theory. Okay, so the figure is Yeah, so this is a question. Uh, for the figure shown below, find the reaction moment and deflection at A. So we have to find the reaction moment and deflection at point A. And here we have to use the Timoshenko beam theory. So we are not supposed to use the Euler-Bernoulli beam theory for this question. So let's begin from its solution. So first of all, draw the FBD for this figure. So this is our beam. Because this is a roller support, so that's because the rotation is restricted here. So reaction moment is acting. So we are supposing M is acting. M is the reaction force here. This is point A and this is point B. This end is fixed. So there is a reaction force also and there is a reaction moment also. Both will be present here. Moment at B and the reaction at B. This is the load P which is already acting at P by 2 at a distance of L by 2 from left end as well as right end. So this is our FBD for this problem. Now coming to the force balance. So here we have two unknowns. Basically we have three unknowns here: reaction force RB, reaction moment MB, reaction moment MA. Okay. So, and for the Timoshenko beam theory we have two equilibrium equations, but here we have three unknowns. So we can't determine all the three reactions in this case. So that's why we have to find only the reaction moment and deflection at point A. Okay, so let's start. So let's start that the coordinates, suppose the coordinate system is at this point. Okay, sorry. Suppose the coordinate system is at this point. So let the origin of the coordinate system at the right end B for this problem. Okay, and using the deflection equation, using Timoshenko beam theory, we have EI d theta by dx equal to mx and dy by dx minus theta of x equal to vx. So here also, as earlier, so here also we have two different moment and shear force expression from these two parts, that is from x equal to 0 to L by 2 and from L by 2 to L. So we have different expression for the moment, reaction moment and the shear force. So therefore we are splitting this question into two parts. The first part is from the left end, that is from 0 to L by 2, and the second part is for the right end, that is from L by 2 to L. So first case is as mx and vx will have different expression for x less than L by 2 and x greater than L by 2. So we consider two cases. First case is for x is greater than equal to L by 2. So let's consider the case when x is greater than L by 2. So I am drawing the beam. This is our origin, as I already mentioned that the right end is our origin. So x is greater than L by 2 is like something here. This is our x. Here it is fixed, so your moment is acting and there is also a reaction force. This is P acting at L by 2 distance, as this is also fixed. Here also roller support, so reaction moment is there, so moment about A. Point A, this is point B. Now using FBT, using force and moment balance, we compute the value of these unknowns. Summation over Fy equal to 0. What is Fy? RB minus P equal to 0. Sorry. So we consider the case here. So this is our beam. This is moment acting. This is moment about A. This is Vx. Here also moment at x acting. So using this, we have Vx equal to 0, and we are considering this as a positive direction. Moment about left end equal to 0. So minus ma plus mx equal to 0. So mx equal to ma. Now for x is less than L by 2. So in this case, we have this is less than L by 2. This is load P is acting at a distance of L by 2. Here also a moment is acting, moment about A and moment about P. Here is a reaction force acting, RP. This distance is x, which is less than L by 2. This is point B and this is point A. So considering this cross section, so this is P acting, this is load P acting. Here there is a reaction moment MA. Here there is a reaction moment Mx. This is shear force Vx. So summation over Fy equal to 0, which gives us P plus Vx equal to 0, Vx equal to minus of P. Okay. Vx equal to minus of P. Now moment, summation over moment about left end is equal to 0. So this is minus of Ma, start from the left end, right end Mx minus P into L by 2 this distance is L by 2, P into L by 2 minus Vx into L minus x minus Ma equal to 0. So it becomes this is actually equal to minus p. So it becomes mx equal to my ma minus p into L by 2 minus x. Okay. So here we see that in the expression of mx, ma is unknown. So we have basically here two unknowns, mx as well as ma. So we need one extra boundary condition to solve for the displacement. So boundary condition here is for x is less than L by 2. If x is less than L by 2, there is no deflection here. So y at 0 equal to 0 because it is fixed. You can see because this is our origin, we consider here as origin. So for x is less than L by 2, deflection is 0 and slope is also 0. And for x is greater than L by 2, we have slope equal to 0. Now for x equal to 0 to L by 2, that means x is less than L by 2. We are using the Bernoulli equation, that is E into d theta by dx equal to ma minus p into L by 2 minus x. On solving this, we get mx ei into theta of x equal to max minus pl by 2 into x, L by 2 into x minus x square by 2 plus c1. Now using this boundary condition, theta at 0 equal to 0. Theta at 0 equal to 0, which means max, it becomes also 0, which means it gives us c1 equal to 0. Now theta at x equal to max upon ei minus px upon 2ei into L minus x. So this is expression for theta, and using the second equation, that is dy by dx minus theta of x equal to minus p upon kga. This is basically v, so here vx is coming out to be minus of p, since vx equal to minus of p, that's why we are right here. So this is the case, vx equal to dy by dx. This here we are using the second bending equation for Timoshenko beam theory. So yes, so this is the case. Now dy by dx minus theta of x equal to minus p upon kga, and we found the expression for theta of x, so it becomes dy by dx equal to max upon ei minus px upon 2ei into L minus x minus p upon kappa ga. Okay, so y of x will become, basically this is a deflection, ma upon ei into x square by 2 minus p upon 2ei L into x square by 2 minus x cube by 3 minus px upon kappa ga plus c2. Now to find out the c2, we are using the boundary condition, that is y at 0 equal to 0. Y at 0 equal to 0. Using y at 0 equal to 0, so it becomes y at 0 equal to c2 equal to finally 0. So c2 coming out to here is 0. So here we found the deflection equation that becomes C2 equal to 0. So y of x will finally become, just copy it from here. So y of x become this one. Now for x is greater than equal to L by 2, that is x equal to L by 2 to L. So here we are using the same equation, that is the Timoshenko beam equation. EI d theta by dx equal to MA, because here you can see that mx is coming out to be MA. So therefore EI d theta by dx equal to MA. So theta of x equal to MA upon EI into x plus d1. Now you are using the boundary condition at theta at L equal to 0. Theta at L equal to 0, we will get 0 equal to MA, that is here, from here we will get d1 equal to minus MA L upon EI, which becomes theta of x equal to MA upon EI into x minus L. Okay, now we are using the second equation for Timoshenko beam theory, which is dy by dx now here you can see that we found for both, that is at x equal to, for x is less than L by 2, we found the slope theta, that is theta of x, we found for theta of x for the left end, that is x equal x from x 0 to L by 2, and the other end, that is x L by 2 to L, and at the edge, that is at x equal to L by 2, both should have the same value. So at x equal to L by 2, theta of x from L minus L by 2 minus equal to theta of x from L by 2 plus. So it becomes L by 2 minus max minus mal upon 2ei equal to mal upon 2ei minus pl square upon 8ei. Okay, because here theta is given by ma ei into x plus d1, and this is the plus value, that is from the right side, that is from L by 2 to L, and this is the minus, that is from less than L by 2. So from here we find the value of MA, that is PL square by 8. So this is the value that we find. Now we are using the second part of equation for Timoshenko beam theory for L is greater than L by 2 to L, that is dy by dx minus theta of x equal to Vx. And what is V here in this case? So here V is given by 0. Why? Vx upon kappa Ga. Yes. So Vx equal to minus P for the first case, and from L by 2 to L, Vx equal to 0. So yes. So dy by dx equal to theta of x. And what is theta of x here? So dy by dx equal to ma upon ei into x minus L. So y will become PL upon 8ei into x square by 2 minus Lx plus d2. Okay. So this is the value of d2 PL is upon 8EI x square by 2 minus Lx plus d2. Now to find out the value of d2, we know that the deflection, that is y, must match from both the sides, that is from x equal to 0 to L by 2, that is at x equal to L by 2, at x equal to L by 2, y at x L by 2 minus, sorry, plus equal to y at x L by 2 for the continuity, for the deflection continuity, L by 2 minus. So from here we will get PL upon 8EI L square by 8 minus L square by 2 plus d2 equal to PL cube upon 64EI minus PL cube upon 24EI minus PL upon 2 kappa GA. Okay. So from here we will get d2, which is equal to PL cube upon EI 1 by 64 plus 3 by 64 minus 1 by 24 minus PL upon 2 kappa GA, which is again equal to minus, sorry, PL cube upon 48EI minus PL upon 2 times kappa GA. So this is the value of d2. So the final deflection equation at x equal to L will become, so basically the question is to find the deflection at the A, that means from the at x equal to L. So at x equal to L, y at L equal to PL upon 8EI x square by 2 minus Lx plus d2 at x equal to L. And when we compute this, we will get y at L equal to minus PLQ upon 24EI minus PL upon 2 kappa GA. So this is the final expression that we get for the deflection at point A. Now the next question is to find moment at A. What is moment at A? So moment at A is given by PL square upon, sorry, moment at A is given by PL square upon 8. So this is moment at A. I think I have done some mistake here. So theta at L by 2. MAL upon 2EI minus PL minus L by 2. Okay. Yeah, so MA is equal to PL upon 8. MA is equals to PL upon 8. So this is the final answer for this question. So in this question, we have solved the question that is given in the problem here. So here we have to find two different things. That is first deflection at point A and moment at point A. So we have found that question. We have found the answer for this question. That is moment at A is given by PL by 8 and deflection at A equal to, this is deflection at A. Okay, is given by minus PL Q upon 24 EI minus PL upon 2 kappa GA. So yeah, so this is a very good question related to Timoshenko beam theory. The question number 3 that I solved earlier is based on the Euler-Bernoulli beam theory, and question number 1 and 2 based on the shear center, concept of shear center. So this is all about today's session. I hope you enjoyed the session today, and please reach out to me if you have any doubt related to this session. You can also write in the chat box in the YouTube channel, and you can ask in the next meeting, which will be scheduled in the coming Friday, which I will take, which is based on the week 11. So thank you for joining today. That's all for today. Bye. You can now leave the meeting.